All right, everyone. This is a video to cover the material in the integrated rate law activity. All right. And we've previously looked at what are called the differential rate laws. And we saw yesterday, or previously, that there are three different versions of that differential rate law. So let's imagine a reaction where A decomposes into B and C, all right? And we saw that there are three possibilities. There's rate equals K times concentration of the reactant to the zero power, and that's referred to as a zero order reaction. We know that we could have rate equals K times concentration to the first power. That's known as a first order reaction. And we could also have rate equals K times concentration to the second power, and that is known as a second order reaction. All right. So in other words, what that means is that these powers that we write here, right, this power is known as the order. So if it's zero order, that exponent is a zero. If it's first order, that exponent is a one. If it's second order, that exponent is a two. All right. Now, it turns out, for weird math reasons that require calculus, which is beyond the scope of this course, that there's another way to write these rate laws that's known as the integrated rate law. And we can come at those in a number of ways, but one of the best ways is that if you imagine doing an experiment in which you were collecting data and graphing the concentration of the reactant versus time. If the reaction happens to be zero order, you'll find that this will go down in a linear fashion, straight line, until it reaches zero. So that's for a zero order reaction. The concentration versus time will give you a straight line. That is not the case for a first order reaction. For a first order reaction, what we find is that the concentration versus time gives us a curved line, and in fact, it's an exponential drop in concentration. Right? So, and then second order looks a lot like the first order when you graph the concentration versus time. It turns out it's what's called a power law, but not that important at the moment. Will be in a second. But it decreases a little less drastically than the exponential, but it does decrease in a kind of curved manner like this. So the real trick here is how do we distinguish a first and a second order? Because they kind of look alike when you graph the data in this way where you're graphing concentration versus time. The way you do that is that we're going to do some math to make the graphs come out to look like straight lines. So this is pretty easy for zero order because it's already a straight line. So for zero order, and man, my axis is terrible there. Here, let's try that again. For zero order, the concentration of the reactant versus time, just a straight line, easy peasy. Okay. It turns out for first order reactions, what we have to do is we have to graph the natural log of the concentration, ln, natural log of concentration versus time. Okay. And if you're not super comfortable with logarithms, for right now, it's just a button on your calculator. It's called ln. Looks like an I. It's an L, I promise. The ln versus time is going to give you a straight line. Like that. And if you're graphing a second order reaction, it turns out you have to graph 1 over the reaction of 1 over the concentration of the reactant versus time. That will give you a straight line. Okay. This one actually goes up. My bad. Try to get a reasonable sized eraser here to. Oh well, I tried. Okay. So this one will look like this for second order. Okay. All right. So every reaction is different. Sometimes even at different times the reaction is different. Sometimes at different temperatures it's different. But so every set of conditions, reaction, time, reaction and temperature are going to be a little different, and you're going to get a different answer And the only way to know which of the three answers you're going to get is to do the experiment, okay? But it turns out if the reaction is zero order, you'll get a straight line when graphing the concentration versus time. And we can express that as an equation in the form, so this is a straight line, so we're doing y equals mx plus b. So the y is equal to negative of the k. It turns out the slope of this line, remember slope is m, the slope of this line is the negative of k. So negative k times t, the x, plus the initial concentration is going to be the equation for zero order. For first order, it's going to be the natural log of the concentration is equal to negative kt plus the natural log of the initial concentration. So now the slope of this line is again negative k. And for second order reactions, it's 1 over the concentration equals kt plus 1 over the initial concentration, right? So here the slope of this line is equal to the rate constant. So the slope is always equal to either the positive or the negative of the rate constant, which is no big deal because you just make it basically, whichever the positive version is going to be the rate constant, okay? So these up here that we did a minute ago, or that we've done previously, these are going to be known as the differential rate laws. Okay. So these three up here are the differential. These three down here are known as the integrated rate laws. Okay. And notice that the difference between the differential and the integrated, the differential contain the word rate, so how fast is the reaction actually occurring, whereas the integrated contain time in them, right? So that's how you always know which one you're dealing with. Are you dealing with time or are you dealing with rate? And if it's rate, it's differential. And if it's time, it is integrated. The best way to understand what's really going on here is to work a practice problem. So if you will look in the course packet on page 78, page 78 in the course packet, there's a problem number 8, and I'd like you to pause the video right now and do that problem. Okay? So in the packet, do question 8 on page 78. Pause the video. When you think you've got it done, hit play. I'll give you one piece of advice. When you're finding the column that's labeled ln of nv, you just take the nv value and you take the natural log. Some of your calculators, you type in 0.5 and then hit ln. Some of your calculators, you hit ln and then 0.5. You've got to figure it out. And that far right column is just 1 divided by the 0.5 or whatever the value is in that concentration column. So pause the video, work the problem. All right, so hopefully you've paused and worked the problem and didn't just gloss through it, because if you don't work it, this is not going to make a lot of sense. This is the answer you should have gotten. So these are your values up here for the concentration, ln of the concentration, 1 over the concentration. Hopefully you got those numbers. And then I've made graphs of each of them, the concentration versus time, natural log of the concentration versus time, inverse of the concentration versus time. And you'll notice that the concentration versus time is a curved line. The 1 over the concentration versus time is a curved line, whereas the natural log of concentration versus time is a straight line. That means this particular reaction at this temperature, whatever temperature it's being carried out at, this reaction is first order. And what we can do is, and we know that because the graph that turns out to be linear has natural log in it. You do just have to memorize that if the concentration versus time is linear, it's 0. If the ln is the concentration versus time is linear, it's first. If 1 over the concentration versus time is linear, it's second. You just have to memorize that. But you'll have the equations available to you on an exam, but you have to know which one goes with which order. So here we know the reaction is first order. We can find the slope of this line by doing delta y over delta x. And if you do that, which I think you are supposed to, you should get that the rate constant is 0.5. A goofy thing about the units, whenever you take natural log for reasons I'm not going over right now, natural log makes all the units cancel out. So the y-axis is unitless. So the k value is actually 0.5. Is this minutes? Yeah. So it's 0.5 minutes to the minus 1 is the value of k here. All right. If you're still a little shaky on this, I want you to go ahead and try to do the exercises for this activity, because I think you'll find that that will help with kind of solidifying everything in the activity. And then, of course, if you need any help, shoot me questions.